basically, based on my experience, I think I really benefited from my PhD training and also my postdoc training. I basically provided all the opportunities for students basically to, for example, present their work after they have the paper published and also interact with their peers and other basically researchers in the field. Yeah.
Okay, that's great. I think we 9:34 or 5. Prasha, you can say a few words, but general announcement. Then we can start the panel introduction. As I briefly mentioned that we will keep the introduction probably in 10 minutes, and because some time in Asia is quite late, and we will start our presentation no later than 9:45. Prasha, you can go ahead.
Thank you, Tom. Just a very brief statements or announcement about EML. EML was established at the very end of 2014. So this is 2024. We're going to celebrate the 10-year anniversary by doing a couple of things. One, we are planning to organize a special symposium at the SCS meeting in Hangzhou this year. Second thing is we're planning to have a special issue published in celebration of 10-year anniversary of EML. So I'd like to thank all of you for supporting EML on behalf of our editors and editors-in-chief, and also keep tuned and look for those announcements. And I hope that you can submit your papers, best papers, to the special issue, and you can participate in the 10-year anniversary symposium at the SCS meeting. Thank you. Back to you, Tom.
Okay, thank you, Prasha. First, welcome everyone to join the EML webinar for the Young Investigate. And it's our great pleasure to see you here. And we have a fantastic panelists and also many attendees here. I think let's have a brief introduction of the panelists. I will first start with Xueju's PhD advisor, Professor Suman Xia. And then I will go through the order of the screen, and I will call your name and you can give a brief introduction. So, Professor Xia, probably you can first say a few words.
Hello, everyone. Good morning, good afternoon, good evening. I'm Suman Xia from Georgia Tech. I'm a professor of mechanical engineering. My area of research is experimental mechanics of multi-physics materials.
Okay, I will call the name based on the order on the screen. First one is Zhang Jia. Zhang.
Oh, hi, this is Zhang. I'm a special editor of EML, and I'm in charge of organizing the new EML webinar. Yeah, thank you. Thank you for all your support on the new EML webinar. Thank you.
Next one is Ge Qi.
Hello, I'm Ge Qi, or you can call me Kevin. And I'm from Southern University of Science and Technology in China. And what I'm doing is smart materials and 3D printing of smart materials. So we all call it 4D printing. And my research is mainly focusing on developing advanced 3D printing apparatus and developing printable functional materials, and then also design the 3D printed structures for many applications such as software robotics, flexible electronics, and many others. And thank you all, and looking forward to Xueju's talk.
Professor Xia.
Me?
Yeah.
Okay. I'm Jimmy Xiao. I'm from Nanyang Technological University in Singapore. I'm one of the editors-in-chief of EML. I'd like to thank all of you for supporting EML.
Jie.
Hi, good morning, everyone. I'm Jay. I'm currently an associate professor in the Department of Mechanical and Aerospace Engineering at the NC State. So my research more focused on the mechanics and design material structures, especially in the mechanical materials and also some soft robotics. Yeah, thank you. Yeah, look forward to your talk.
慧禅赵。
Hi, everyone. My name is Hui Chen. I'm from Tsinghua University, currently an associate professor at the Department of Mechanical Engineering. I'm so happy to see my advisor, my PhD advisor, Rob Shepard, is here. Hi. It's such a surprise. And I work on soft robotics as well as artificial muscles and the soft sensors. It's so great to join you. Thank you.
Thank you. Next one is Nicholas.
Thanks.
Hi, I'm Nicholas Lucas. I'm an assistant professor at Cornell University and in the Civil School of Mechanical and Aerospace Engineering, and my research is in computational mechanics and multiphysics. And I see quite a few people, JJ's next door in the office next to me.
Next one is Jun'er Zhu.
Hi everyone, this is Junior and I'm assistant professor at Northeastern University and I work on batteries and mechanics. I benefited a lot from Xueju's work and her work with Professor Shumanxia. Thank you.
Next one is Pu Zhang.
I'm Pu Zhang from SUNY Binghamton University. I mostly work on soft conductive materials recently. I work on the manufacturing, modeling, simulation all together. Thank you.
Next one is Abden.
Hi everybody, I'm Abdon Pena Francesc. I'm an assistant professor in material science and engineering at University of Michigan. And it's great to see everybody. Excited for Xueju's webinar.
Next one is Shaoting.
Hi everyone, this is Shaoting Lin from Michigan State University. So my group trying to use molecular design theoretical modeling for understanding the processing structure property relationships of a material. Great to see everyone and look forward to Xueju's talk.
Halim.
Hi everyone, my name is Halim Kusumatmadja. So I'm a professor in the Department of Physics at Durham University in the UK. So my group does modeling and simulation. So in particular, we're interested in soft matter, biophysics, and multi-phase flow. So I look forward to Xueju's talk.
Robert.
Hi, so I'm an associate professor at Cornell in mechanical engineering, and I continue to live off of Hui Chen's success in my group. And really, I'm trying to work on soft sensors, soft actuators, and soft power systems, but still on the hunt for the killer application of it.
Thank you. Jingjie.
Hi everyone, I'm Jingjie You. You can just call me JJ, and assistant professor in Cornell's mechanical and aerospace engineering. So we work primarily on computational nanomechanics of bacterial cells and biopolymers.
Yung Zhu. Yeah.
Oh, sorry. Hello everyone. Yang Zhu from North Carolina State University. My research includes mechanics of nanomaterials and also some applications of nanomaterials from soft electronics and more recently some soft robotics. I have known Xueju for many years. I think Xueju, the first time we met, you were a graduate student, right? At maybe one of this SEM, right? Maybe the Southeast Graduate Student Conference or something like the SEM event.
Yeah.
So I'm glad to see your career has developed so well, right? You started from experimental mechanics, but now I see you are doing a lot of related to materials, structures, also devices, applications, anything. That's great. Look forward to your talk.
Thank you. Thank you.
Sulin Zhang, next one. Sulin, we cannot hear you very clearly. It's better, but still not very good.
Yeah.
No.
Maybe we should just.
why my camera doesn't work today. So in here from Wednesday. Yeah, I'm one of the editors for Extreme Mechanics Letters. Nice to see you guys. Thank you for your support to get out. Looking forward to the support.
Thank you, Sulin. Robin.
Oh, hey, this is Xueju's neighbor. We're not so far away. Robin from Northeastern University. I study mechanics and materials. Study a lot of adhesion, adhesives, and liquid crystal elastomers. A little bit architecture materials and energy materials nowadays as well. So I think I've known Xueju for probably 6 years. We talked a lot, and we visit her lab, and we also collaborated. It's very nice to see his works here, and look forward to that.
Next is Jin Yang.
Hello, everyone. Here is Jin Yang from the Aerospace Engineering Department at UT Austin. My research works on the experimental mechanics, including DIC, DVC, laser disc cavitation stuff. Looking forward to Xueju's talk. So excited about you.
Thank you.
Guangchao Wang.
Hello everyone. My name is Xueju Wang. Currently I have a postdoc at Texas A&M University. So previously I was a postdoc in Professor Zhang's group. So that's the reason I'm here. So nice to see everybody here. So
thank you. Jingda.
Hello everyone. I'm Jingda Tang from Xi'an Jiaotong University. Now I'm a associate professor. I also work as a special editor for EML. We launched a special issue on machine learning and mechanics. If you are doing this aspect, please submit your article. And we also, as Jimmy said, we also plan to launch a special issue celebrating the EML's 10 years anniversary and a symposium at SES. So welcome to participate in this event. And I know Xueju because she is also in the group of special issue. I'm looking forward to her talk. Thank you.
Thank you.
Wang Liang.
Hello, everyone. This is Wang Liang from Syracuse. I'm a colleague of Teng in the same department, in the MA department here. So I work on adhesion mechanics, small materials, and also soft robotics. I think I came to know Xueju when she was a postdoc, I believe. Still on the job market, I remember that's like 2016 or something. Over the last few years, he has developed so much, and I look forward to your talk, Xueju. Thanks.
Thank you, Wang Liang.
Okay, thanks everyone. I think it's time to introduce for this EML webinar. I'm Teng Zhang. I'm associate professor at the Mechanical Aerospace Engineering at Syracuse University. I have known Xueju for many years. I think we first met at the SES at Brown. That's 2013. I also want to mention that we both graduated from Dalian University of Technology. That's also Sulin's the same university. And I will not repeat all the Xueju's CV. Xueju is now assistant professor in the material science and engineering department in the University of Connecticut, and also affiliated with biomedical engineering. You can see her research is highly interdisciplinary. She has received many awards like NSF Career Awards and ONR Young Investigator Awards, and also very importantly, this EML Young Investigator Awards. That's also why we have this webinar today. And without further delay, I think Xueju, you can go ahead to share screen, start the presentation. We are looking forward to your talk.
Thank you, Teng, for the nice introduction. Let me share my screen. Okay. Oops. Why? Can you see my screen?
Yes.
Okay, great.
Yes.
Okay. Thank you, Teng, for the introduction. It's always very nice to be introduced by a collaborator and a friend. Also, thanks EML for the invitation. It's such a great honor for me to present my work in this great platform, especially in front of my mentors, colleagues, friends, and collaborators. So the timing of this webinar also provides a great opportunity for me to summarize and reflect on what I have done after I started my independent career for the past few years. So as the title indicated, today I'm going to share with you our work on morphing materials and multifunctional structures and electronics for potential applications in intelligent systems. So intelligent systems are an exciting and emerging field. When we talk about intelligent systems, we can easily think of our familiar biological systems. For example, an octopus, which can change its shape and color to adapt to their environment. The Venus flytrap is another example. So it can catch the prey when its sensitive hairs in the inner surfaces are triggered by the prey's movement. Of course, there are many other examples. For example, the spiders, which will always find you. It sounds a little bit scary, but this is because it can detect even very quiet movements by using its more than 3,000 string sensors distributed across its body. Last but not definitely not least, our human body, right? The human brain is such an intelligent system that there is so much work going on trying to unlock the mystery of a human brain, including the electrical signals and more recently, the brain chemistry. So understanding and mimicking the performance of those intelligent systems are significant for many engineering applications. For example, for performing tasks in unstructured real-world scenarios, disease diagnosis and treatment, and many others. So how do intelligent systems work? Basically, they first sense or interact or interpret their environment by using their sensors, and then they can diagnose and respond by moving, changing their morphology and colors. Those information can be further stored and processed so that they can acquire experience and evolve over time as this loop continues. Then the question is, how can we mimic or eventually even go beyond the performance of those intelligent systems that exist in nature? So to do that, for example, first to sense the environment, we need to integrate sensors, usually in a soft, flexible manner for operation in ambient environments, but also in harsh environments. For example, extreme temperatures, large hydrostatic pressure, high salinity, corrosive environments in the ocean, because if you think about the environment that a lot of creatures like an octopus lives, right? It's a very basically harsh environment. Also, basically, we want to have a stimuli responsive materials and structures that can respond to the environmental stimuli, including temperature, light, humidity, pH, and also mechanical forces to basically interact with the environment, right? Also, it is important to adapt to the environment, which can be realized by, for example, programmable, reconfigurable structures, adaptable stiffness, color, texture. Additional features include self-healing, self-regulating, degradable, pouring systems, right? Computing. So it has to be admitted that intelligent systems are very complicated. So for the past few years, I have been trying to basically address some of those aspects in my group. So basically, we work at the intersection of materials, mechanics, and multifunctional structures and electronics. More specifically, we study three major directions. One is active materials and reconfigurable structures, including stimuli-responsive materials like liquid crystal elastomers that I will discuss later, and chip memory polymers. We design and develop reconfigurable structures based on those materials and also based on mechanical multistability. In addition, we also develop functional structures to interface with biology, including 3D electronics for the monitoring and the stimulation of engineered tissues, and also 3D microfluidics in a shape programmable manner to mimic basically many biological features. In addition, we also develop soft, flexible electronic sensors, including physical sensors like temperature, pressure, and strain sensors, and also chemical sensors like salinity sensors for applications in wearable devices like smart bandits for accelerating the diabetic foot ulcer healing, and also for sensing in the harsh ocean environments. So in today's talk, I will cover some of those aspects due to the time limit. More specifically, I will discuss our efforts of morphing structures based on active materials, liquid crystal elastomers, and also based on mechanical multistability. And then I will discuss our efforts in sensing, especially in harsh environments. Okay, so morphing materials and structures are promising for many applications like soft robotics, artificial muscles, and other intelligent systems. Based on the deformation mechanism, typically morphing structures can be divided into two categories. One is based on soft active materials like hydrogels, magnetic composites, liquid crystal elastomers that can respond to external stimuli like temperature changes, magnetic field, and humidity to change their shapes and therefore their functionalities. So those types of soft active materials have enabled a lot of interesting and exciting opportunities and structures. One potential limitation is that they require persistent external stimuli to maintain the deformed state. For example, for the magnetic composite structures, when we remove the magnetic field, the structures will return the original shape. So this may cause some inconvenience and also make it less energy efficient for some applications. So in the past decade, people also developed morphing structures based on mechanical multi-stability. For example, origami and origami structures that have multiple stable states that they can be reconfigured among. So an advantage of this type of morphing structures is that they can maintain the deformed state without the need for persistent external stimuli because its state is locally stable. So next, in this talk, I will discuss our efforts actually for both categories and also our efforts by leveraging both mechanisms to create innovative morphing structures. So I will start with morphing structures based on soft active materials, in particular liquid crystal elastomers. So liquid crystal elastomers are a type of smart materials that combine the rubber elasticity of polymer networks and the orientational order of liquid crystals. I think we have also EML webinars given by Kaushik and Robin on this basically materials. So this material has attracted much attention for applications including artificial muscles and soft robotics because of their unique properties, including soft elasticity and large reversible shape changes. So the reversible shape changing behavior is closely coupled with a reversible state transition of liquid crystals, also called messagens. For example, to program messagens on liquid crystal elastomers for actuation, we first align the messagens along a direction called a director into a state called a pneumatic state. Heating above a temperature called isotropic clearance temperature will disrupt this messaging order into an isotropic state and drive the macroscopic shape changes. So this state transition is reversibly can be reversibly realized so that we can have the reversible shape changing behavior upon cooling and heating across the isotropic clearing temperature of the structure. So you can see that the reversible shape changing behavior is closely related to the messaging alignment, right? So current alignment techniques include mechanical alignment, like stretching and bending for relatively simple shape changes, and also surface patterning that can enable very complicated patterns, but is usually limited to thin films below 100 micrometer thick. People also use external fields, for example, magnetic forces for the alignment of messages. More recently, people have developed this 3D direct ink writing 3D printing to create 3D LCD structures where messages are aligned along the printing path due to extrusion-induced shear stress. So those techniques are great for creating diverse 3D LCD structures for shape morphing, but still it's very challenging to create, for example, hollow open mass 3D LCD structures like helices and spirals for many applications like soft robotics and other intelligent systems. So here we developed a facile and versatile strategy for the spatial alignment of LCEs to create previously inaccessible 3D LCE structures. So this is based on basically a so-called compressive buckling technique that was originally developed by Zhang, Yonggang, Yihui back to a few years ago. So basically, we first laminate the 2D LCE patterns onto pre-stressed elastomer. So here, the LCEs were synthesized by the classic two-stage thioacrylate macro-addition reaction methodology because of its ease of use and also the reliability. So we applied a thin layer of adhesive between the LCE and the elastomer substrate to at selective locations to create a strong bonding called bonding sets. And then by releasing the precision, we can geometrically transform the 2D patterns into the 3D architectures due to these compressive forces. So during this process, the messages are spatially aligned into their pneumatic state because of the compressive strain in the material. So UV exposure induced additional cross-linking and also permanently programmed the messaging alignment, which provides immediate access to freestanding 3D LCE structures. By heating and cooling across the isotopic clearing temperature, which is 62 degrees for this material used in this study, we can morph the structure between 2D and 3D configurations reversibly. Okay, so here are the experimental and finite element analysis results of the 3D LCE structures, as well as the dynamic shape morphing behavior of the structure. So we also characterized the thermal response of the structure, basically how fast it can respond to the thermal stimuli. Basically for this particular structure, it's a few seconds. And we also characterized the maximum actuation strain of the structure, which is shown to be proportional to the pre-strain in the assembly platform. So here are a series of experimental and simulation results of the 3D LCE structures enabled by this technique, including those that can mimic, for example, butterfly, a cage, and also we presented their reversible shape morphing behavior. Basically, you can see the 2D pattern and the 3D structure after heating and cooling. So those structures are basically previously inaccessible by using techniques, for example, 3D printing and surface patterning. So they can basically expand the structure space of those 3D LCE structures. So also you may notice that for some structures, even with a small amount of compressive strain, we can enable this messaging alignment and also can enable the shape morphing behavior. So we were very curious about how the messaging alignment looks like within these complicated 3D structures. So when we looked at the existing techniques to characterize the messaging alignment, we found basically the WAX and FTIR techniques, two commonly used techniques for the messaging alignment characterization. But unfortunately, they require 2D thin film samples for testing, which is not available for our complicated 3D structures. So to estimate the messaging alignment degree in the 3D structures, basically, what we did is we first calculated the strain distribution within the 3D structure, and then we basically performed the testing on 2D thin film samples corresponding to the strain levels. This way, we can basically estimate the strain, the order deformation in the 3D LCE structure. Also, this testing is in collaboration with Professor Kai at CU Denver. So I will skip the details, but basically, we can see that the alignment degree, which is quantified by a parameter called the order parameter in LCEs, is proportional to the strain levels. Also, for example, at a strain level of 12%, you can see it has an order parameter of 0.377. For your reference, this order parameter is usually below 1. So basically, it suggested a notable alignment of polymer chains within the LCE sample already with a small amount of strain level. Okay, so in addition to basically creating 3D LCE structures using pure LCEs, we also added other functional elements, for example, magnetic particles to the material for two purposes. First is basically to enable the very compliant structures, because as you know, the strain energy required for the compressive buckling is proportional to the Young's modulus of the material. So adding magnetic particles can enhance the basically mechanical properties of LCE structures. The second purpose is to enable magnetic actuation, which is fast and remote beyond the thermal actuation. So we can see that the modulus of the magnetic LCE composite increases almost linearly with the magnetic particle fraction. Also, we showed that adding magnetic particles does not change the shape morphing behavior when it is below 50 weight%. So here are the a few examples of magnetic LCE composite structures which are very compliant and inaccessible with the pure LCE materials. Okay, to demonstrate the potential applications of LCEs, here we basically developed a biomimetic soft LCE robot from magnetic LCE composites that can respond to both magnetic and thermal actuation for a series of biomimetic behaviors. For example, jumping, crawling across an obstacle, and crawling under a narrow crack by morphing between the 2D and the 3D configurations, and also basically deliver cargo by dissolving a water-soluble tape that was used to secure the basically object onto the robot. Okay, so far I have discussed our efforts basically in creating previously inaccessible 3D LCE structures and 3D magnetic LCE composite structures. You may notice that most of the structures are symmetric, and also they have uniform stiffness. As I mentioned at the beginning, for intelligent systems, a lot of times they need adaptable stiffness and asymmetric geometries to basically mimic those intelligent systems that exist in nature. So next, basically, I will discuss our efforts to locally tailor the stiffness and the morphing behavior of reconfigurable LCE structures. So here we still adopted the basically buckling technique to use a ribbon structure as an example for the study. But here, instead of blanket UV exposure of the entire structure, we used a photo mask to enable selective photopolymerization. So this, for example, for this ribbon structure, we used a photo mask to cover half of the structure. Then in the UV exposed region, you can see that the messages are highly cross-linked, and also their alignment are permanently programmed. Well, in the UV in the covered region, then the messages still maintains a lightly cross-linked state, and also the alignment is not programmed. Okay, so in addition to the difference in cross-linking density and messaging alignment in the UV exposed and covered region, they also have a stiffness difference of almost 50 times in the highly and lightly cross-linked regions. So basically, it can create stiffness heterogeneity within the same structure. Okay, so after being removed from the substrate and heating, you can see that the structure can basically morph to the 2D configuration because of the isotopic pneumatic state transition. But when it cools down, what is interesting is that driven by the shape morphing in the UV exposed region, which is highlighted in purple, the structure morphs into asymmetric structure with basically heterogeneous stiffness, with the purple region basically almost 50 times stiffer than that of the gray region, which is lightly cross-linked. So basically, this asymmetric interesting structure is achieved by harnessing the molecular material structure interactions. By selective photopolymerization, we can create a difference in cross-linking densities and messaging alignments. Then they can decide the stiffness heterogeneity in the material level, and the material level stiffness heterogeneity and the molecular level messaging alignment can synergistically create basically the local shape morphing behavior of the structure. So here basically are the experimental and finite element analysis results of the local programming of LCE ribbon structures, which can start from an arc shape and then morph to basically this asymmetric structure after selective programming. So the simulation is in collaboration with Teng, which is conducted by using model change feature in Abacus. We also characterized basically qualitatively characterized the messaging alignment at 2 locations to evaluate basically the messaging programming. In addition, we also studied how basically, for example, by changing the cross-linking densities and areas and locations of the messaging alignment can give us basically different morphing behaviors and final configurations. We can see that starting from the same original structure, we can obtain basically quite different final configurations with different basically stiffness heterogeneities. In addition, the technique can be extended to other more complicated structures as shown here. Also, in addition to creating or tailoring the local basically properties and shape morphing behaviors, we can further utilize the unprogrammed lightly cross-linked regions for sequential programming. For example, take this a simple rod-like structure as an example. When we program the first corner, we can achieve basically the this structure with a square shape, and it has a reversible shape morphing behaviors between this shape and the rod-like structure. We can further program the second corner to achieve basically different final shapes, and of course we can continue to program, for example, third corner. Basically, starting from the same structure, we can have this multi-purpose functionalities. This sequential programming can be further expanded to basically membrane of LCEs. Here, as an example for demonstration, we basically sequentially programmed membrane LCE to sequentially display the facial features, for example, first the nose and mouth and eyes, the whole face, basically. So as I mentioned at the beginning, in addition to shape morphing, for some creatures like octopus, they can also change their color for behaviors like camouflage to adapt to their environment. So here, by adding thermochromic dyes into LCEs, we can realize shape morphing and color changing LCEs within the same structure upon heating and cooling. For example, for this octopus-like structure, it can morph to basically colorless and 2D configuration for activities like camouflage behaviors. We also incorporated magnetic particles for adaptive motion. For example, it will have different swimming speeds under the 2D and 3D configurations. In addition, we can realize biomimetic motion and camouflage behaviors by basically using these thermochromic LCE structures. Okay, so so far I have discussed our efforts of morphing structures based on soft active materials, especially liquid crystal elastomers. We discussed how we can spatially align the materials for previously inaccessible structures, how to create stiffness, heterogeneity, and color changing capabilities for potential applications in intelligent systems. So as I mentioned at the beginning, those soft active materials are great for creating a lot of interesting morphing structures. But one potential limitation is that they require persistent external stimuli to maintain the deformed shape, which may cause some limitations in some applications. So here, next, I will discuss our efforts in another type of morphing structures that is based on mechanical multistability. So in the past decade, people have made significant progresses in this field. There are a lot of works, including those from the audience. Despite intensive studies, still there are a few critical challenges remain in this field, especially when asymmetric and complicated structures are involved. The first challenge is associated with the presence of multi-stable local minimum configurations. They could affect the stability of the targeted stable state under perturbations, for example, environmental noises, or trap the structure in an intermediate state during reconfiguration. So we need to increase the energy barrier of those targeted states and eliminate unfavorable local minima. Another challenge is associated with the complicated transition pathways from one state to another, especially when the two states are separated by other stable and transition states. In addition, remote, locally controlled, and rapid reconfiguration are usually desired for many applications. So here I will present a set of design concepts and strategies to address those challenges. by using an integrated experimental and simulation approach. So here, basically, we first use a 3D table-like structure as an example, also as a model system for this study. So the structure is compressively buckled from basically ferromagnetic composite thin films. After buckling, we can use a portable magnet to deform it into basically another state. So to our surprise, basically, even for this very simple structure, we can find very interesting, also distinct stable states by using experimental and simulation efforts in collaboration with Teng and Halim. So basically, we found that for this structure, it has 3 distinct stable states, in total 9 configurations. With the first state is the symmetric as buckled structure, as you can see from here. The state 2 has basically one arm of the table structure deformed. Also, it has 4 configurations corresponding to 4 different orientations. For state 3, it has basically 2 arms, an additional arm deformed. It also has basically 4 configurations corresponding to the 4 orientations. So basically, we used a discrete shell model to basically model the nonlinear deformation of the structure, and also by minimizing the energy of the structure, can locate the stable states of the structure. Okay, so we further studied basically how the material and the geometry parameters affect the number and the configurations of the stable states. So here is a design phase diagram. In terms of the number of stable states, as a function of the 2-dimensionless ratios of energy scales, gravitational, stretching, bending, basically, which contribute to the energies of the buckled structure. Okay, so we can see that we can divide the regions into 3 regimes. When the 2 energy scales are large, basically we have 3 states, as we discussed earlier. As they decrease, you can see that state 2 actually disappears or becomes unstable. When we further decrease this energy scale, we only have 1 state, basically the buckled up state. So we further validated the phase diagram by using basically experiments efforts. So we can see that experimental results and simulation results agree with each other pretty well. So this diagram provides very important guidelines for achieving a well-controlled number of stable states, or for removing undesired stable states for many applications. For example, if state 2, which means basically this 1-arm buckled down state, is undesired, we can tune the parameters to stay within this blue regime, so that we only have state 1 and state 3 available. Okay, so in addition to identifying the stable states, for those structures, reconfiguration pathways, especially along the energy minimum pathway, is very important for many applications. So we further basically studied the reconfiguration pathways by using the reconfiguration from state 3, basically with 2 arms buckled down, to this state 1, basically this as buckled structure, as an example. So we explored how the pathways will vary as a function of basically the geometry parameter by using this in-plane size of the structure as an example. So here is basically the diagram showing the variation of the energy barriers against this geometry parameter. So basically we have 3 regimes. I will talk about the details in next few slides, but basically in the first regime we have 2 pathways, path 1 and path 2 exist. In the second regime, as the geometry decreases, basically we have still 2 pathways, but the second pathway is a little bit different because state 2 is no longer available. And then when the dimension further reduces, basically we only have one path. So in the next few minutes, I will discuss basically more details about those pathways. Okay, so when basically this this geometry is in this regime, as I mentioned, there are two pathways transitioning from state 3 to state 1. So here are the energy as a function of normalized path length. So the first pathway is basically is a so-called direct pathway because you can say it's from this state 3 directly to state F. Here is the video corresponding to the basically the simulation results. We can see that it's basically does not bypass any other intermediate states. A second pathway is basically a pathway that first goes to this state 2 with basically one arm bucked down. Here is the video. You can see from state 3 first comes to this state 2, and then goes to this state 1. So for the energy barriers, when you compare the two pathways, basically the energy barrier for path 1 is larger, which means that it requires a larger energy input, although it's a direct pathway. The path 2 has a smaller energy input, but it needs to bypass state 2. So there is a potential that it may be trapped at this state, and also it needs more magnetic manipulation, as you can see from the video. So it's kind of like a trade-off, depending on what applications you want, right? Smaller energy or it's more direct pathway. Okay, so when the dimension reduces, we basically have comes to the second regime, where the state 2 is no longer stable. So you can see that we still have two pathways with similar shape evolutions. Path 1 basically directly from state state 3 to state 1. This path 2 here we use a path 2 star because this state 2 is no longer stable. You can see that it follows similar shape evolution, but here it no longer bypasses the state 2. Also, we found an interesting crossover within this regime. Basically, it's a critical, like a point that decides which path has a smaller energy barrier. As we further reduce the geometry of the structure, you can see that we only have one path, basically the first path, the direct pathway. For the second one, basically it disappears because we can no longer reconfigure the structure from that pathway. So those basically studies clearly show that basically first the transition pathways are very complicated, and also the integrated experimental and the simulation methodology can provide a very important guidance regarding the choice of the pathways. Also, you can see that the experimental and the simulation results agree with each other very well, which further indicates the fidelity and the reliability of the methodology. Okay, so the methodology, the developed methodology is not limited to, for example, 3D barcode asymmetric structures. Here, for example, we also applied the methodology to an asymmetric bistable unit, which basically can morph from the initial state to this asymmetric final state. So the minimum energy path for this asymmetric bistable state is not that straightforward, actually, but based on the studies, we can successfully transition the shape following the pathway following the pathway predicted in the modeling. So here is basically a video showing basically how we can use wood strap to basically reconfigure the structure from the original state to the final state, which would not be available if we directly use pure compression. Okay, so we developed a methodology. We further expand the study to origami-inspired multi-stable structures, where basically actively controlling the number of stable states and their reconfiguration pathways also is also a challenge. So here we basically tune the two control parameters, the number of creases and compressive strengths, because they are easy to tune, and also they are more practical for many applications. So here basically we used a relatively simple structure for the study. It's basically Riemann structure with creases. But even for this simple structure, you can see that it has multiple stable states. For example, it has one set peak, buckled, two peaks, and twisted two peaks. It has a very rich basically phenomenon involved. So here is a design phase diagram. Basically, in terms of the number and configurations of the stable states as a function of number of creases and strain levels. So we can see that the number and the configurations of the stable states highly rely on the number of creases and the strain levels used for the assembly. So basically here we studied how the strain and the number of creases affect the multi-stability separately. I probably will skip the details due to time limit, but basically you can see that as the number of creases increases, the number of stable states first increases and then decreased. This is understandable because at the beginning it's a continuous structure, right? When the number of creases increases to a certain level, it's also approaching the basically continuous level. Similarly, the strain level also significantly affected the number and the configurations of the stable states. This also indicates that we can basically by tuning or manipulating the strain level and number of creases, we can tune tailor the number and basically configurations of stable states. So as a simple demonstration, we basically developed this origami-inspired soft robot under magnetic actuation for basically potentially be applied in intelligent systems. So in addition to basically employing the multi-stable structures for intelligent systems like soft robotics, we also basically expanded its application to other fields. For example, the manipulation of droplet or fluid control. For example, here it's actually 2x3 ribbon array, crystal ribbon array, but it has basically 3 stable states. And then basically we can use the stable states to tune the water droplet flow. For example, when it is in the so-called, we call it a center peak, in this state, the water droplet will be pinned within the structure. But when we use a magnet to tune the state to this basically left peak, you can see that the water droplet can actually flow. So here is a video showing how basically by tuning the state of the structure, we can control the water droplet flow using a magnet. Okay, so that's basically how we can use state change to tune the water droplet flow. But not all cases will result in that manipulation. For example, if you tune the center peak to a so-called red peak here, actually the water droplet will be still trapped within the structure. So by using basically those stable structures, we can actually we can actually tune the basically fluid flow for potential applications. So here, basically, we characterized the critical angles for the water droplet to flow under different stable states as a guideline for potential applications. So this work is still ongoing, but I think it's very interesting. So I'd like to share with the community, and I also welcome comments and suggestions from the community for this basically solid fluid interactions with the structure. Okay, so so far I have discussed our efforts in morphing structures based on liquid crystal elastomers and also mechanical multistability for potential applications in basically multifunctional structures and intelligent systems. So as I mentioned at the beginning, so for intelligent systems, sensing in ambient and also in harsh environments is very important. So in the next couple of minutes, I will basically discuss our efforts in this space. So sensing in the ocean is very important, not only for intelligent systems, but also, for example, tracking the fish, ocean animals, and also to understand the ocean environment. The reason why I'm interested in this field is because I found that conventional ocean sensors, for example, sensors that measure the conductivity, temperature, and the depth of the ocean, they are very big. They also require high pressure chambers and seals to operate in the large hydrostatic pressure in the ocean. Therefore, they require large power supply and has a large footprint, which makes it impossible to be integrated with many platforms. So the emerging soft electronics in the past decade has basically provided an alternative solution. Basically, soft electronics, they are made of soft and incompressible materials. They can potentially withstand large hydrostatic pressures and eliminate the need for pressure chambers. Therefore, they can substantially reduce the power requirement and the size of the sensor. So despite its great promise, there have been very few studies in this space. So for example, current flexible electronics, there are many developed for example, biomedical devices which operate in the low pressure regions, usually, for example, on the order of a few or tens of kilopascal. But for ocean sensors, they need to operate in large hydrostatic pressure in the ocean, which requires a large pressure tolerance. Encapsulation of the sensor is another important aspect. Current flexible electronics are usually encapsulated with polymers, inorganic materials for operation in ambient conditions, like for wearable devices, or for in biofluids, like implantable devices. But for ocean sensors, they need to survive the salinity environment and also the large hydrostatic pressure. Also, they need to satisfy the desired measurement range, for example, the high pressure, temperature, and salinity. Another aspect is the interface between sensors and the data transmission, because when it goes to the underwater environment, the currently or typically used, for example, Bluetooth and the near field data transmission are no longer working. So how to make sure the sensors can transmit the data reliably is also an important aspect. But in this talk, I will share our work to address the first three aspects. So basically, here is a schematic of the soft sensors we developed. Basically, they are composed of active materials, gold thin films, encapsulated with multi-layer basically polymers that I will discuss later. So they can be potentially integrated with many platforms for potential applications. So here is an optical image of the sensor. So it's much smaller compared to the traditional ocean sensors. Basically, they're on the millimeter scale, and also they're flexible. In addition, to enhance the encapsulation capability of the sensors for operation in a harsh ocean environment, we basically developed an oil-infused rough elastomer layer, which is basically prepared by coating PDMS onto a rough mold, and then by infusing oil into the rough PDMS to basically create this layer. So this SEM image shows that basically the oil-infused rough PDMS is highly porous, and also it sacrifices some of the transparency actually compared to pristine PDMS because of its roughness and porosity. So I will discuss the encapsulation capability for this material later. But basically, we first characterized the sensor in ambient conditions. We can see that it has a high linearity and a good cyclic performance. To simulate the large hydrostatic pressure environment in the ocean, we custom build basically a pressure vessel, where we can control the pressure and the temperature simultaneously for the testing of the sensors. It can achieve a maximum pressure of basically 3,000 psi, equivalent to 2 kilometers in the ocean. So we can see that for the sensor, basically when it is tested under a hydrostatic pressure from 0.1 megapascal to 15 megapascal, which corresponds to 1.5 kilometers in the ocean, yeah, it still maintains the linear basically relationship between the response of the sensor and the temperature. Also, the hydrostatic pressure has a negligible effect on the performance of the sensor, which can be further basically indicated in this plot where you can see that the sensor performance basically maintains a constant value under different pressures. Also, it has basically good cyclic performance under hydrostatic pressure. In addition, the morphology of the sensor, including the backside and the front side, basically have negligible changes after the testing. Okay, so we further tested the encapsulation capability of the temperature sensor, basically by putting the sensor in salinity environment. We can see that the sensor can survive the salinity environment for more than 7 months, which is very interesting and basically impressive compared to the control study by using the pristine PDMS, which can only survive for basically a few days in the salinity environment. Okay, so we basically also, in addition to temperature sensors, measuring the conductivity, salinity in the ocean environment is also very important. So here we developed this soft salinity sensors composed of 2 gold electrodes, also based on the lithography. So they have displayed very good flexibility and stretchability. So one thing I want to share with the community is that when we tested the sensor, characterized the sensor, my students and I found that the sensor will be corroded, or there will be some dilution of electrodes. Even we tested using multimeter. So at the beginning, we were very confused. And we went back to this electrochemistry of gold. We found that gold will react with chloride ions at a voltage above 0.8 volt. This leads to the basically corrosion and dissolution of electrodes. This is further confirmed by using this so-called LSV for this scanning of the electrodes under different basically salinity levels. You can see that after the testing above this 0.8 volt, we will have some corrosion of the electrodes. So that's very important for the testing and the design of the sensor, because you need to operate below 0.8. Another issue we found that is polarization effect under the DC current, DC voltage. This is because under the DC voltage, there would be accumulation of those ions near the electrical surfaces. That will cause a sharp decline of current, making the sensor very insensitive. So basically, after addressing those two issues, one is basically the voltage issue, and the other is basically the polarization effect. We further studied the effect of frequency, magnitude of AC voltage, and the effect of sensing areas on the performance of the gold-based salinity sensors. And we come up with this, although rough, but hopefully useful diagram as a guideline for basically the use or the application of gold-based sensors, especially in the chloride ion environment. Okay, so to summarize, I think through this talk, I shared our work on morphing structures based on active materials and also based on mechanical multistability. We basically addressed the spatial alignment and also stiffness, heterogeneity, and color changing capability in liquid crystal elastomers in hope of creating basically biomimetic color changing and shape morphing intelligent systems with basically controlled stiffness and shape morphing behaviors. In addition, we also basically shared our efforts on morphing structures using mechanical multistability, which can bypass the limitation of the requirement for persistent external stimuli. I shared basically our experimental and theoretical approach for studying the continuous structures and also origami structures, as well as our ongoing work for fluid control. In addition, the sensing in harsh environments, which is also important for basically mimicking the intelligent systems. I hope through my talk you can basically learn something about this space. I also hope that I think more people can join me to basically to explore this space. So finally, I'd like to thank my current group members, collaborators, and the funding sources. Last but not least, I would like to thank my mentors over the years, especially Professor Xueju Wang, my PhD advisor at Georgia Tech, and Professor Zhang Rogers, my postdoc advisor at Northwestern. They have been supporting me over the years through the different stages of my career. Really appreciate that. And also many others, including, for example, Professor Xueju Wang at the University of Washington, Professor Minzhou, and many others. With that, I will stop here and open the floor for questions and comments. Thank you very much for your time and attention.
Thank you, Xueju. You cover so many exciting topics in 1 hour, from fundamental science to the very important challenging applications. So I think it's now time to open the floor for questions. As Professor Xia mentioned, I think to track the question, the panelists, you can raise the hand and then you can ask the question. If several of you raise hand at the same time, I will try to decide, use my eye, the order I will type on the chat and who will ask first. And we also welcome attendee to ask a question. You can type your question or raise your hand, and we encourage the student and the postdoc to ask a question. Suman, yeah, you go ahead.
Okay. Can you hear me now?
Yes.
Okay, good. Okay, fantastic work, Xueju. Well done. Actually, the material systems you worked with me in graduate school were all hard materials. Since then, I know you have moved to the other end of the material spectrum into very soft materials. It's great to see that you are continuing to excel in your current work. I think the talk is very fantastic, very informative. I just have a very general question about the first part of the talk on liquid crystal elastomers. So what's a biocompatibility like for these elastomers? Do they have any potential applications for like implantable devices?
The potential applications, right?
Yeah. Are these elastomers fully biocompatible? Like they can be used to make like implantable devices?
Yeah, thank you for the question. So I think not all liquid crystal elastomers are biocompatible, but indeed there are some biocompatible liquid crystal elastomers. Also, with transition temperature of body temperature 37 degree. So I saw people use the shape morphing behavior to tune the alignment of, for example, shells. For potential applications. Regarding implantable devices for their potential applications, I think by using biodegradable, biocompatible liquid crystal elastomers, I think that's basically one opportunity, I think. Although I have not seen people exploring that space yet, but I think that would be a good opportunity.
Early stage.
Right. Yeah,
Yes,
early stage.
Thank you.
Perfect. John Rogers, you're next.
Oh, hey, Xueju. Hey, everyone. That was a wonderful talk. It was really extremely well done, and a wonderful, I think, combination of fundamental research in mechanics and nonlinearities and material science, but also some really targeted applications-oriented research as well. And so I love that blend of science and technology. So I have two questions. Hopefully that's okay. One is sort of specific around your research. So I'm just now returning from a Gordon research conference on robotics. And so there's a lot of interest in soft robotics and micro scale, or let's say sub-millimeter scale robots. And so I was really interested in your little walker. That was a pretty neat demonstration. I just wonder if you have additional ideas and plans to do research in that direction of small scale robotics. So that's my specific question. And then my other question is just a general one, which is that as a junior faculty member, you've been so successful with research funding and research productivity and student mentorship. And I know there are a lot of younger researchers on the call, and any kind of words of advice or lessons that you've learned, as a new faculty member starting a group. I think the audience here would be very interested in hearing your thoughts. So those two questions.
Thank you, John. Also, thank you for joining from California. So regarding your first question, yes. So we, for example, ongoing work is basically just a specific example. We're trying to develop a self-digging robot that can, for example, swim in the ocean and then dig into the sediment to explore the ocean. Also, you plan to integrate electronics to measure the sediment chemistry, for example, in situ. That's basically just one example by integrating the morphing materials and structures with electronics to a level of intelligent systems. Although we know it's still far from the fully intelligent systems, but that's one example. Yeah. So the second question, yeah, thank you for your comments. It's so inspiring to hear that. So I think for me, at the beginning, I would say, at the beginning, actually, I was also very worried when I started my independent career. I would say, find something you think that's impactful and just do it. That's my starting point, I would say. But as my research program evolves, I think I can basically better integrate different elements and also by collaborating with people, for example, Teng and other people, we can basically elevate, I would say, the program to a different level. Yeah. Thank you.
Yung, next.
Okay. Well, excellent talk, Xueju. I have also two questions, if that's okay. The first one is specific questions, right? For your the last part of your talk, your underwater pressure sensor, right? So you put you said some encapsulation, right? I was curious how maybe I missed it. You said some oil infused PDMS, that the oil infusion can be effectively encapsulating the electronics.
Right. Right.
Okay. Okay.
Yeah, basically the oil can be trapped within the pores of the rough elastomer. Therefore, it can serve as an encapsulation layer for the fluid, for example, the ocean water.
Because in order to infuse the oil, you need to make it porous.
Right, right.
I think that when you open it, make it porous, I don't know, you think the oil can fill all the pores?
That's a good question. So basically, that's kind of like a assumption. Of course, we also performed a very thorough studies during the infusion. So so we basically assume the oils filled all the pores.
Okay. Well, but your experimental results certainly already prove that. I was just curious because you have to open the pores and then fill it with this, but it seems working very well. The other question is, it's a more general question. Well, I see both of your advisors just asked the questions, right, from your PhD postdoc, Xueju Wang and Zhang, right? From what I see, I know Xueju Wang's work very well. Of course, I also do know Zhang's work, right? So I think when you work with Xueju Wang, you were working on experimental mechanics, right? Like a DIC for battery applications,
right?
If I remember correctly. And of course, with Zhang, you started working on materials, right? I think the buckling, the 3D buckling, right? Maybe that's one of the piece of work with Zhang. When you work with Zhang, you probably work on multiple projects. But anyway, to me, that is a very big change, right? It's a very big change. I know a lot of students, right, when they graduate, when they find postdoc positions, they try to stay in a comfortable zone, right? They try to work in similar areas, right? At least they know what they can get out of the postdocs, right? They can get a few papers and so on. So I think, but in your case, I see because it's very different. So you must be very brave, right, to work across that. So what was your thought at that time?
Thank you. Thank you for the question. So so I would say it was kind of like it happened probably because of several reasons. One reason is that when I started my independent career, everyone asked me, okay, how do you differentiate your research from your previous advisors? So that's a sad note, but that also made me think about it. But I think so basically, as you know, I had a background in chemical engineering for my bachelor degree, and then PhD training in mechanics. And then when I joined Zhang's group, it was a pretty multidisciplinary research. So I think through this process, I think it also gave me basically kind of like an impression that basically I can work at this interdisciplinary research. The experience also made me kind of, I would say, brave to dive into this new field. I think.
Thank you.
Okay, very nice talk, Xueju. So I just have an interesting technical question. Your last part was pretty interesting. I never heard that. I know you have been working on this. So do you have any thought on underwater actuation, especially under the high pressure for these soft robots? Of course, these are traditionally thought as incompressible rubbers or materials, right? Soft materials. But since if you have deep sea underwater, very high pressure, then maybe there could be some interesting fluid structure relationship. Have you ever thought about this? I know, for instance, Professor Ke Liu, another collaborator of mine, he's also working on this, and he told me he observed something interesting, but it's not completely understood at this time. So could you share some comment on that?
Sure. Yeah. Thank you, Robin. Yeah, that's a good question. I think soft actuator in the ocean, or in general in underwater environment is is a challenge, I think, considering basically the water environment and also the temperature control. We have not. I mean, we have been thinking about this space, but we have not explored a lot. But I think you know, for thermal actuation, it was not that easy, especially in the cold water, deep in the ocean. So magnetic actuation, it has limited basically distance, right? Actuation distance. I think I saw people use, for example, electrical actuation. I think the work, the Nature paper by Tiefeng Li at Zhejiang University, I think they used basically this electrical actuation. I think that's one option. I think I was also thinking because at the different depths of the ocean, the pressure is different. Maybe by leveraging the pressure difference, you can design some fluidic structures to basically take advantage of the basically pressure difference. That might be one option. Yeah. So yeah, still I think that those are just some thoughts, but I think we're also still exploring the this space. The panelists, the audience, welcome to jump in.
That was very nice. Thank you.
Professor, yeah.
Muted.
Thank you. Very nice talk, Xueju. Really enjoyed it. I noticed that Zhang had his seatbelt on when he turned his camera off. Then you asked the question. See, Zhang has his seatbelt on. You asked the question, how did you change from Schumann's group to Zhang's group? Completely different topic. Zhang was trying to say, fasten your seatbelt when you join my group. Anyway, so I do have a couple of technical questions, mainly related to challenges. One is one challenge for all morphing structure, which you are interested in. You showed very interesting morphing structures, but most of them have a gradual change of curvature. Then you ask yourself the question, how can I have a sharp change of curvature in a morphing structure? We actually recently did some work on plants. There's a particular plant called Elsevier or something like that, which has embedded in the plant structure, plant leaf structure, what we call hinge cells. That turned out to be critical for this particular plants, for the leaf to form zigzag shape under dehydration. So I wonder whether there are similar mechanisms or strategies people can use to in the shape morphing structure to form sharp corners rather than gradual change of curvature.
Interesting behavior. So basically, by dehydration, they can form this zigzag shape. Oh, very interesting. So I think
so the paper actually was a theme revision we submitted to PNAS about this. The central question we asked was, how do we form sharp corners, essentially? We learn from plants to do that. Yeah. Go ahead. Sorry to interrupt you.
No. Yeah, thank you for sharing that interesting work and the phenomenon. Yeah, so I think one way probably, is to create, for example, creases like origami structures. That may be the easiest want to think of, I would say, by creating, for example, creases, by leveraging the difference in the thickness at the different locations of the structure to create sharp corners. Yeah, that's what I can think of and have been working on. Yeah, others I have not explored other, for example, options for you. It's still within the structure, but sharp corners, right? Sharp corners. Yeah, I think origami would be one option. There may be also other interesting opportunities there. Yeah.
Okay, good. Another question I have is another challenge for soft materials. The actuation is generally relatively slow.
Yeah.
And you showed one potential strategy to overcome that, which is multi-stable structure. So when it jumps from one stable configuration to another stable, or to one equilibrium configuration to another equilibrium, that jump can be fast. But it also actually there's some recent work that showed that that jump itself depends on the loading rate. Suppose you have the critical condition for jumping. This is a work by Mingchao Liu and Dominic Villa. They show that if you move the structure extremely slowly towards the critical condition for jumping, it actually has a different sharpness of the jump. So when you move it very slowly, the jump is very sharp. If you move fast, it jumps. The jump is much less sharp, much gradual. So the dynamics over there, I think it's a very rich area. In your case, because you're interested in these morphing structure, I think there are a lot of things that can be done in that area.
Yeah, thank you for sharing that. That's very interesting. Yeah, I think currently we still we have explored basically the state transition, but we have not explored a lot of regarding this dynamic transition. I think that's interesting. Actually, I think Teng is also here. So we kind of realized that when we used the multi-stable structures to manipulate, for example, the droplet flow, actually it's not only the interaction between solid structures and droplet. There are, as you mentioned, a very rich phenomena of dynamics there. Basically, how fast the droplet can move, how fast basically the structure can deform. There may be a competition between the structure deformation and the droplet motion. Yeah, I think very interesting phenomenon. Also, very interesting research space for people to work together.
Indeed, a rich space. Actually, Zhang mentioned the robotics or soft robotics community. I'm sure they are extremely interested in such type of phenomena, and maybe especially the dynamics of those submechanics of configuration. Thank you. It's a wonderful talk. Very stimulating.
Thank you.
Thank you. I think next question is Jie.
Hi, Xueju. Yeah, enjoy your talk. It's a really wonderful talk. So I have a short question. I see John is having breakfast. Actually, I also in the California. I haven't had a breakfast yet, so I'm gonna run for the breakfast. Otherwise, they're gonna take all the food away. Okay, so my short question here is so for the first part, right, about the LCE, the freestanding or LCE structures, actually I'm pretty excited about that. Because for me, it's for us. I mean, at least for me, it's very hard for us to generate this kind of freestanding, LC structures. So, do you have any support layer, in those kind of, say self-assembly, this kind of structure there?
Oh, when we assembled the structure, yes, we did. We have an assembly platform or substrate, basically pre-strained elastomer substrate. But after the structure is assembled, we removed the structure from the substrate to form the freestanding structure. Because of the ship locking programmed alignment of messages, the LCE can basically maintain the freestanding structure.
Okay, because we are generating some these 3D freestanding structures, but because of the self-weight, sometimes because it's so soft, actually gonna collapse by itself. So that's why I'm asking you the question.
Oh, is it because of the stiffness, the thickness? Probably, the strain energy of the structure is proportional to the modulus, the cubic of the thickness and the dimensions. I think you probably, I'm not sure the exact geometries you are using, the parameters you are using, but probably you can play with those parameters to.
Yeah, I feel maybe it depends on the size also. Yeah, that's for sure.
Yeah, size, thickness, and modulus. Right.
Okay. Yeah. Thank you. Yeah.
Thank you for joining from California, and also thank you, Zhang. It was very early in California time.
Okay, great.
Thank you, Jie. Zhang Jia, you can go ahead.
Thank you, Xueju. Very wonderful talk. So you mentioned Tiefeng Li's work on deep sea soft robots. So I also collaborated with him on that project. So I'm very interested in the sensor work you mentioned. So for your temperature sensor, so my question is, what's the temperature resolution, or how sensitive your sensor is? What's the smallest temperature change you can measure? Because the temperature resolution, I think, is very important for the application of sensor under sea. So that's my first question, the temperature resolution. My second question is, you also mentioned that the performance of the sensor is not affected by the pressure, the hydrostatic pressure. That's a little bit counterintuitive, because we usually consider a polymer as an incompressible material, but under high pressure, PDMS, I mean, most polymers, they are definitely compressible. So the high water pressure, hydrostatic pressure, can cause a volume change of your temperature sensor. And that may lead to the change of the response of the sensor. I mean, under sea, under high hydrostatic pressure. So can you explain why? I mean, your sensor is so stable under high pressure. Yeah. That's my two questions. Thank you.
Yeah, thank you, June, for the questions. Also, it's great to hear that you collaborate with Professor Tiefeng Li. I think that was a very interesting work for the underwater robots. So your first question is regarding the resolution of the temperature sensor, right? So that's a very important aspect. For our work, basically, we have not, I would say, we have not very systematically studied that yet. At the beginning, it took us quite some time to custom build a pressure vessel to mimic the ocean environment. So we first calibrated the sensor basically regarding the response. I think, but I think you can basically get a basic sense of the gold-based temperature sensors. Basically regarding the resolution, but we have not systematically explored it yet in the large hydrostatic pressure. That's also some actually some work we will pursue along this line. So second question is regarding the performance of the sensor under different basically hydrostatic pressures, right? So I think so basically we I would say we tested the sensor actually for its for each basically pressure, we tested multiple sensors. Indeed, they performed very reliably. But because the pressure chamber is not transparent, we were not able to observe that in situ. I think I saw Professor Tiefeng Li's work. You have kind of like a transparent window to view the performance of the robot, but we have not, I would say, observed in situ. But based on the performance, I think they are basically they will deform under the larger hydrostatic pressure, but that does not seem to cause a significant basically effect on the sensor performance. That's basically the conclusion we have obtained, but it warrants further study regarding basically the details of, for example, whether there is a delamination between layers. Yeah.
Okay, thank you.
Hongyu Zhou.
Hi. Hi. Thank you so much for your talk. So I have a question regarding to the second part, which is the multi-stable and bistable structures. So I was wondering, because you mentioned that sometimes some kind of states will be not stable. For example, the state 2, you mentioned that sometimes it will not stay there. To maintain, so it maintains kind of geometry in the in the state 2. So can I ask, once you met such an issue, if you're trying to make that a state 2 or some kind of unstable state, make it stable. So do you have any methods to trying to improve the stability? Thank you.
Yeah. Thank you for the question. Yeah. I think the answer is yes. So basically, with the design phase diagram, we can basically tune the number of stable states by manipulating the geometry and the material parameters. Basically, we can, for example, tune the in-plane dimension of the structure to enhance the energy barrier and to basically make it stable. That's the short answer. Yeah.
Yeah. Okay. So basically, which kind of part? Because geometry and material, which kind of part is usually very is very commonly used when you tackle this issue?
Oh, I would say the easy way to do it is geometry. Because for a given material, the material properties are fixed, right? So easiest way to tune, for example, thickness or literal dimension of the structure. That's an easy way to do it. That's also what we did actually in the work.
Oh, okay. Thank you so much. Thank you.
You're next.
Okay. Very great talk. I have two questions. The first one is technical question. The second one is a general question. For the first question, I think in your first topic, you use buckling to align the LCE. But if you consider a beam, we teach beam bending. If you bend it, one side is tension, one side is compression. So would the alignment of LCE be different along the thickness direction of the beam? This is the first question. The second question, how could you be so productive? I mean, as young faculty, we have so many things to do, and also to train students, establish research program, get funded, get teaching, every other duties to do. How could you be so productive? Thank you.
Thank you, Pu. Thank you for the question. For the first question, yeah, very good question. So as I mentioned, there are no existing techniques that would allow us to study the basically messaging alignment in 3D. But I think based on the string distribution, I would assume there would be difference across the thickness direction regarding the messaging alignment. Because you can say, as you mentioned, compressive versus tensile. So hopefully, in the future we can come up with techniques for imaging or for analyzing the message and alignment distributions within the complicated structure. The second question that can also related to the question that Zhang asked. I did not talk a lot at that time, but I think I also struggled, I would say, at the beginning. I also struggled. I remember first semester, I basically devoted all my time to teaching. It was a new class. I spent so much time for teaching at the first semester for a new class. At the end of the semester, I feel okay. As a faculty, I haven't written any proposals, any papers, haven't done any research. This is not right. I think during the winter break, there was basically a funding opportunity. A colleague shared with me. Basically, that's kind of like how I started working on a proposal. I think I'm not a quick writer. Basically, on average, I wrote 3 to 4 major proposals that I lead. But for each proposal, I would say I usually spend a lot of time on the ideas and how to basically make it compelling. Second, I think that's for proposal writing. Also, I think I have met great collaborators, for example, Teng. I think we first met at the 2018 MIC conference. We talked about this collaboration, multi-stable structures, and basically modeling experiments. That's how our collaboration started. I think it has been very successful, right? We wrote collaborative proposals and also basically joint papers. I think collaboration is also very important to expand basically my research space. That's also comes back to Yung, the question earlier, how I briefly dived into a different field. I think it's also very important to have great collaborators. Teaching, I think after you taught a few times, I think it will become easier. Student mentoring, I think I'm still learning. I think, as I mentioned at the before the seminar, I'm still learning. But basically, I think this is also the experience I learned from my PhD advisor, Dr. Xia, and also Zhang. I think I basically was exposed to different styles of research. But for my students, basically, I usually closely worked with them at the first 1 to 2 semesters. After that, usually I gave them quite some freedom to basically develop. Yeah, those are some of my experiences. Also, I think usually I devote some focus time for me to really focus on writing proposals and papers, usually a few time blocks in the morning, and then other times kind of like meeting with students. Yeah, so those are some limited experience I have. Still, I think as a junior faculty, I'm still learning actually from great people around. Thank you.
Thank you.
Thank you, Xueju and Apple. Next question is Beijun Sen.
Thank you, Professor Zhang, and thank you very much for wonderful talk, Professor Wang. And I'm a PhD student from Johns Hopkins University, and I have a quick technical question about the bistable unit cell that you presented. So you're saying that the bistable unit cell with the 2 tilted beams can quickly jump from one stable state to the other fully closed stable state only by compressing from one side, which is not realized by like pure vertical compression. Would you mind like further elaborating a little bit more on that? Thank you.
Yeah, so basically by pure compression, you cannot achieve the shape transition from one state to another state. So what we did is actually we combine the compression and the rotation following the MEP minimum energy pathways predicted in the modeling to successfully achieve the shape reconfiguration. Yeah, that's basically what we found. It's not intuitive. It's not intuitive if you just do it by trial and error.
Got it. All right. Thank you.
Next question, Li Hua.
Hey, Xueju. Hey, everyone. Yeah, indeed, a very nice work from fundamental mechanics to a lot of applications showing really a wide spectrum of work. I have a question about your multi-stable states. So you identify, yeah, I may have missed some of your earlier talk, but you identify a finite number of stable states. How are you able to identify them and knowing that you are not missing anything?
That's a great question. So I think basically what we did actually that's in collaboration with Teng here. So we minimized the energy of basically the energy of the structure. So we I would say we cannot say we do not miss any single stable states, but we tried our best to identify all the local minima as a stable states. So this is I can actually I can quickly share my screen for more information probably. So basically this is what we did. So we basically use a discrete shell model to basically model the structure and minimize the structure energy. Regarding the finding the stable states, we used this algorithm, which is very efficient for minimization involving a large number of degrees of freedom. So regarding the structure, for example, for the bulk of the structure, we split it into a number of different regions and give a random force to enable the structure to take different configurations. For example, for the table like structure, we use 8 regions for the structure, and then we repeat the process several hundreds of times to identify different local minima in the energy landscape. Once we found it, we will basically use it as a starting point to evaluate the stability throughout the range of different design parameters. Right, that's how.
I see. So has this work been published or published together with your other work?
Yeah, so this is a part of the paper I presented EML material.
I see.
Also more recently GMPS, the collaborative work with Teng. Yeah.
I see. Okay, thank you.
Do we have other questions? Yeah, I have maybe some general question, 1 or 2, and also some comments related to Professor Xia and also other people's discussing. Yeah, I think Xueju, you did a wonderful work, and your application is to go to the water under the sea, and we also have other extreme conditions like extreme cold environment in the North Pole, South Pole, or maybe go to the outer space, like a morphing structure application to the building. So we may have different challenges, like making the morphing larger and they can sustain wider temperature range. Can you comment that what are the potential strategy to achieve different morphing structure for different extreme applications?
Yeah, thank you for the question. That reminded me a question that my daughter always asks me: would you rather live in the Arctic or in other extreme conditions? So yeah, so I think that's a very interesting question. Also a space to think about. So basically, you mean the application of morphing structures in those extreme environments, right?
Yeah.
I think I have not explored, but I think there are a few aspects to consider. For example, the material degradation under those conditions. Also, their reliability, repeatability. Also, regarding actuation, whether, for example, for LCE, for liquid crystal elastomer, the elastomer, so that I have been working on, the transition temperature is 62 degrees. I think it will be very difficult to actuate it under a very cold environment. You can, for example, change probably molecular information to reduce the transition temperature if you apply it to very cold environment, or probably encapsulated with a layer that can serve as a kind of like a protection or encapsulation layer to basically protect the material or to enhance the efficiency of actuation. I think those are some aspects I can think of. Also, basically, the integration with other functional elements. For example, when you think about it, using it in intelligent systems to integrate electronics there, I think the interface between electronics and those materials in extreme conditions also something to consider, I think, right? I think interesting question, interesting things to think about, I think. Yeah. Thank you.
Okay, thank you. Yeah, lastly, I think I wanted to comment to Professor Xia's question about the jumping speed. I think that's a very interesting question, and also many things that we also learn from nature, the bio-inspired. And Xueju and I, and also Halim, we have been working on the energy landscape for the multi-stable structure for maybe more than 5 years, 6, 7 years. And I think we have been doing mostly in the static loading, we ignore the dynamic effect in the energy landscape. Then we can find the local minima, find the saddle point. I think the energy barrier is probably related to the jumping speed. But like Xueju showed in the talk, there may be multiple energy barrier. So if you load the structure into different speed, one possibility, I think maybe you trigger the saddle point, the transition path in different way, and then maybe one had higher energy barrier, and then you release the energy larger than the other one, so your transition speed can be faster. Or maybe you do not pass the saddle point, you are loading it too fast. You just over the saddle point, you cannot release your elastic energy enough. So this is just my rough thoughts. I think it's a very interesting question. That's also, we are thinking one application for the energy landscape analysis here. I think it's also an opportunity to promote our work. We want the community to be familiar with our work. Hopefully, the energy landscape analysis, like the energy barrier, and this MEP can be related to some real application, like Professor mentioned, controlling or tailoring this jumping speed, or control the jumping direction, jumping height. So that's just something I wanted to follow up as Professor's question. And now I think I can hand it back to Professor Zhang. You can have some like a conclude remark. Then we probably can finish our webinar. Is more than 2 hours. Thank you.
Thank you, Teng. By the way, I mentioned at the very beginning that this is the 10th year of EML, and we're going to have a number of activities to celebrate that. Maybe I should invite Zhang to say a few words about this.
Yeah, it's been quite an adventure to start a completely new journal, and it's been wonderful to work with Jimmy and Zhang and Teng and many others. I think we try really hard to do a great job, and moving papers through quickly and reviewing them at the highest levels of technical diligence. And I think a number of very, very powerful papers have appeared in the journal over this time period. And I think it has great visibility now across the community, sort of satisfying this niche that exists between material science, which is my own expertise, and mechanical science and engineering. And I think the future is very bright, but it requires you guys to keep us in mind when you have great research results. Send them to EML, and we'll expedite the review process and make sure it gets great visibility through these kinds of webinars and cover feature articles. And we are active on social media. And I really have to acknowledge Jimmy as the main leader, and Zhang coming up with really great ideas. And I just help out, where I can. But it is a powerful journal. It's a unique need that it satisfies. And I've been very honored and excited to be involved with it from the very beginning.
Zhang has been very humble. He's actually guiding us through many of the challenges and the opportunities. Thank you very much, Zhang. And I would also like to echo Zhang's statement, especially about young people. I think we see a lot of young people involved in EML. We are extremely happy about this. So thank you all very much for that. Keep participating, keep being part of the member of the team, part of the effort, and we'll make the journal a very successful one. Okay, let me hand it back to Zhang, because he's the person in charge.
So I would like to make a very short announcement about our future EML webinar speakers. So let me share my screen. It will be very quick. Can you see my screen?
Not yet.
Not yet.
Yeah.
Not yet?
Now it's good.
Yes.
Okay, now you can see my screen, right?
Yes.
Yeah. So now we have 3 future EML webinar speakers. 2 of them are the 2023 EML Young Investigator Award recipients. The first one is Evgeny Filipov from University of Michigan, and the second one is the Mingchao Liu, so from University of Birmingham. So he is also one of our special editor of EML, who is in charge of the management of the social media. And the third speaker is Tongqing Lu from Xi'an Jiaotong University, China. So he's the author of one top-cited EML paper. Yeah, so we are still negotiating with them about the exact date of their webinar. So please stay tuned. Yeah, so that's my announcement.
And all EML webinars are recorded, and you can check the YouTube and you'll find all the webinars. You can watch them as you like, and you can review them and watch them as many times as you want. Okay, thank you all. It's a wonderful 2 hours. Very rewarding.
Thank
Let's
you.
give Xueju another round of applause.
Thank you. Thank you. Thanks, everyone.
Bye.
Bye-bye.
Thank you.
Bye.
Bye.
Bye-bye.
Thank you.